So if I talk nonsense, you should stop me. And I thank HOD Professor Arun Kumar Das and Professor Hemant Kumar for the invitation, giving me a chance to talk in front of you. So before I start my classes, I tell my student what is the goal of life. Right? The question is what is the goal of life. So my answer is to learn every day something new. So what we are going to do today is like, this is some old concept. Here we put some topological, means something related to topology. And let's see how topology comes in the picture. Is it okay? So this topic, what happens in US, it was introduced sometimes back, but in India still we are not having this. And some topologists like me, I am a topologist, but I love to do mathematics in some other areas also. So some of us, we are trying to explore this area because, it may give a new direction to have something more meaningful. So, okay, I believe not all of you like topology. So I should say what is topology. Whatever we see, it has a topology. We are wearing some clothes, it has a topology. So what does it mean? Some design, some pictures are there. So that picture satisfies some conditions, and that we say that, okay, it is having topology. So they write something. So what is the important property we consider in topology? Is like, if you take a rubber sheet and you pull it, then it looks like different. But we say that, okay, geometry is different, but topology is same. We'll give some good pictures. So goal of topology is to study the objects, whatever we can see. Now you can say that, okay, we cannot see that many interesting objects. So what are the other objects? We cannot see interesting objects. It's like, because we can see in 3D, but what about other dimension? Other dimension we can see because we can do the calculation. We are mathematicians. Right? So if we do the calculation, we can have many other interesting objects in mind. So what is important things in topology, you need imagination mind. That means you should have thinking power, which we are having. But maybe sometimes we are not interested. But if you have imaginative mind, topology is the best subject to have, to learn. Okay. Let it go back. So this is example what we have. This is like donut, which you can get in several places. And if you are from South India, they say like some medu vada kind of things in them. So in breakfast, and it is a very popular. So what you are going to do, that you push it, but don't create a hole or destroy the structure of the hole. So if you go slowly, you will get like coffee cup. So these two objects, they look like different, but in topology we say that they are same. So up to continuous movement, there is no property we are not destroying, basic properties. Okay, so if you have any question, you should stop me. So some other things, so what is this? It looks like solid ball, so if we put in a place it, so it will be like sphere kind of things. So this connection we already noticed, so this is like hollow pipe kind of things, this is like hanger, and okay, as I told you, to see the pictures in topology, we should have some good mind to think here we can see pair of pairs, and that is related to double torus. So that means we have two torus, they are connected at some point. And this T-shirts, it is related to triple torus. So whatever object we see, as I told you, it has some topology up to something. Chair, bench, it does not matter, but we can give the topology for the structure. Okay? So, and this object comes very naturally. Okay. So that was related to topology, but now what we are interested in real life, we have some places and we are connected, like our home and universities. So every day we are going, so that means we are having some edges. So these edges are there. Now we have little bit abstract mind. What we will take? We will take some nodes and we will decide that, okay, whether there is connection or not. So that gives a graphs. So we can see, given some nodes, we can have plenty of different kinds of graphs. Okay, so this is little bit introduction of the graph theory, or definition of graphs in precisely. Okay, so in this topic, most of us, we are interested in what is data. So this, like, whatever we observe, and that observation, collection of that observation, we can say that that is data set. So what shall we do? Why it is important? We need to understand the data set to get some information. So most of us, what we like to become rich. Right? So we want to do some business, and if we cannot understand the business strategy, then how we can be rich, right? So data set, we need to take the observation, we need to do the analysis. Okay, so these are like something written in English which we can read. So this is like some facts or figures, symbols, and it is coming from like text, images, in various forms it can be. Nowadays this image processing, it is very important. So what we do, like we collect, means like we store it in some places, and then we try to understand how the data looks like or what application it gives. So this is the usual way to do whatever statistical method is there. So we take the raw data, then we try to keep it somewhere. Then what we do, like observation. Okay? So processing observation, then we have this analysis, and then we can get some information. So this is a pipeline for the data. This is the usual sense. So I took the pictures from this website. Okay. So next two slides contain several things. Most of the things I don't know. So this, because I left statistics after BSc. Okay, so this is like volume data, of how much big it is, and what are the structures it can be, how we can keep it. So structured data, semi-structures, open. So these are like all things, all the terminologies we know, like the social media posts, emails, chats, messages. So all the terminologies we know. So this is like data types. So several, there might be many more. Okay. But how, why? So what is the usual methods and techniques? There are something we use in data mining, all these topics also. I am not, I mean, I know a little bit, but not too much. But this one is like all of us, we know it. We studied in BSc and MSc, some statistics course. Okay. So this time series test. Okay. So this part goes the usual way to analyze the data. Now, so these pictures we know. So this was known shape for the long time back. This was by statisticians. So what they did, they took the data points and they tried to do the regression line and try to compare. However, we have this statistician Anscombe. So what he observed, he tried to find some data. So he took this data set. If we see the x value in the first three data sets, they are same. Y values are different. So here 8.9. For the fourth data set, the x value is different from the others. Okay. So if we see this picture, we may think that the statistical parameters will be different. However, we have surprising things. So if we take mean of x, so for each of them it is same. If we take variance, we know the definition. So this is exactly same. Mean of y up to 2 decimal places it is same. The variance is also same. Correlation between x and y up to 3 decimal places they are same for each data category. Right? So we should be like surprised. The data set looks like different, but if we apply the classical method, we are getting same result. Then how to distinguish that data set? Okay, so that may say that, okay, let's try to plot those data set in the XY sheet. If we do that, then we get these pictures. So pictures may look like different. I mean, actually it is looking different data set. But how to capture the information? Now, having one similar class of data set which gives the same kind of statistical information, from there somebody can produce as many different class of data set which looks different, but they give the same parameters, statistical parameters. Okay. So what to do? So it gives the idea, okay, we should have different concept. So what is that? What we should find next. So if we have some abstraction, then what we should find next. So can we have something more advanced shape? So that shape was like regression line and some data point. And so can we have something little bit more advanced shape? Okay. Can we have some other question also? So given this data point, whether we can have more information, whatever information we are getting, can we have more information from there? I just put the name neural data because from there we can have many networks. Okay? So our brain network, it has, if we subdivide and how they are working, we will get million network because we have million neurons, right? Okay. So the question, I mean, if you want, you can try to make more question also, but these are the basic questions we should have. Now to answer this, how we can answer it? So that means what we discussed in the beginning, that topology discussed about the properties of the shape. So if we want to have advanced shape, so that means we need to bring back some topological notions. Okay. So this is another way to get some graph. And as you notice that if we are having more nodes and more interactions between them, then we will get more complicated data. But this gives the graph, right? So in the previous case, what it was, it gives the graph. But we want to have whether the network has some shape. So can we have some more topological tools to answer those previous questions? So whether we can have some shape. Okay, now up to this, is it okay? What is our goal? Okay. So we have some data set, and then we want to have some shape of the data. Okay. Why it's not going? So around 2000 or 2002, some people they started to answer these questions. and it has some components which are known as persistent homology and persistent module, persistent diagram, and they found that it will be much more useful than whatever result we had. And that subject is called topological data analysis. So roughly I will say what is the pipeline, then I will discuss it broadly. So first thing is we need to get some data set. So that means it is a finite. Okay, we can have infinite, but whether we can handle it, we cannot do the computation very nicely. So we'll take the finite set. So if we have finite set, what does it mean? See, it's just a point, collection of points, right? So where that collection of points will be meaningful if we consider these points in some metric space. So that means there are some activities between them. So that metric is important. So it does not matter. It is not always the case that it has to be the Euclidean metric, but some other metric also. So having that metric, we can have some properties which will give the graph structure. Okay. So this, having that graph, what we can have some algorithm to have filtration. Yes, the simplicial complexes, so another new terminology which I will introduce. So from the data set we had graph. From that graph we could have simplicial complexes. This is higher dimensional generalization of the graph. And from the simplicial complex, so if we have simplicial complex, we get the topological object. So corresponding to data, we get the simplicial complex, that is topological object. And now topological data analysis means we need to study that object topologically. Okay. So if we have this topological and geometric information from the data set, then we can build the homology. So this topological or geometric features, it does not need to be always homology or cohomology, but some other things also you can think about it. People nowadays, they are doing like topological complexity, persistent topological complexity. That is also another thing. I believe that, personally, I believe that will be the correct way to do the topological data analysis. This is one way, so there is some other ways also. But I choose this way because there are plenty of problems to say. And the other one is still developing. Okay. So now if we have that information, what we want to do? We want to do the computation. And how we can do the computation? We have to put that algorithm in a machine language, so that the machine will do the work. So the fourth stage is for that. So it has to put in a machine so that it will give the answer. So that means it is related to the machine learning problem. Okay. So here we can have this. So what machine learning models we should have, so that we will get the information about the data. Okay. So I took these four pipelines from this paper. So this is an interesting paper which gives a very brief survey about this data analysis. Is it okay? So we have four components. One is data set, from data set to how to get the graph structure, from graph structure meaning like with metric, if we have having metric, then how to get the simplicial complex. I will introduce all of them again. And then if we are having simplicial complex, that means we are having a topological space. Now for the topological space, we can do whatever we want from the topological side. Okay? But that will help the topologist. What about the applied people? So applied people will be happy if we can do machine learning. Okay? Then you tell your coding that, okay, I am doing this coding and this will be the fastest coding or like fastest algorithm. Applied people will be happy. Okay, so n simplex. N means like positive integer. So this is nothing but convex hull of some points which satisfy some properties. So what is the example is like closed interval. All of us know, like triangle, solid triangle, containing the interior point. That is called 2 simplex, and tetrahedron is 3 simplex, like that. But mathematically we can just say that okay, this is the definition. It should satisfy this condition. The convex hull of n plus 1 many points in general position is called like n simplex. Otherwise, you know that if we are given finite set, then the convex combination of the finite set is like convex hull. Right? Okay, so this is the definition. So definition, if we do little bit geometry, so this one zero-dimensional things we can consider. So these are like tetrahedron. The definition of n simplex, okay? Okay, why n simplex is important? Because we can see tiles everywhere nowadays. So if you see the floor, we have tiles. So tiles is like rectangular kind of thing, but you can make it triangle. So if we are having some object and locally we want to know, so how we should, what will be the best process to know the manifold, right? Locally or globally. Locally, if we can fit something very nice, so what is the nice object? This is the nice object. So we fit it together so that it will be covered by these tiles. Right? So tiles means this n simplex. And that kind of things is called like simplicial complex. So we will define the simplicial complex. So it is nothing but it is a collection of n simplices or any dimension, 0 dimension to some n dimensional. If it is finite dimensional, it should satisfy some property. So that means the overlapping should not be like this. It should be like in the boundary. Otherwise, if it is overlapping in a bad way, then we cannot do the calculation. Right? We cannot say that, okay, how much overlapping is there. But if it is overlapping very nicely, then we can say that, okay, its property is calculable. Right? We can do the computation using that. Okay. So this definition, okay, maybe many of you didn't see, but I will pause for a few seconds. Maybe one example is good. So I will go back and forth. So what it is doing, this triangle and this head. So if we see the intersection of this, it is a case of both. So here, if we take this triangle and this triangle, so they are intersecting along this edge. So if it satisfies very nice properties like these tiles, then we say it is a simplicial complex. Okay. It's okay, but the mathematical definition is this. You know, what I feel in mathematics like is good because whatever we observe, we try to fit in such a way that we can apply it in many places. So we have some observation, putting the tiles together, we made like, and we know English because our ancestors were like quasi-British, so we know English. So we just write some English sentences, meaningful English sentences. Okay. It's okay, definition of simplicial complex. So we just need to remember that tiles are putting together very nicely. That's the simplicial complex. And if we do it, it will look much more nice. Okay. So what can we see from here? Suppose nowadays what we see, wherever we go, some like sculptures will be there, which looks like this. Right? So you can thicken it. So homotopically, it's the same thing. As I told you, whatever I see is like topology, nothing there. And now my friend from analysis, they may say that, oh, no, you need to give the exact map. Okay, we can give it, but for the time being, we are not interested in that. Oh, the time is going. Okay, we have time. So now we will have interesting concept. It is called simplicial homology. So it takes time to digest the meaning of simplicial homology, but I will try to go very slow. all of us, we know ring, concept of ring, right, or module. So what we have, this is a simplicial complex. Simplices which satisfy some condition. Okay. Okay. So we take these I-dimensional simplices, we just consider them as a like variable. So this AI, and we take the formal sum. What do we mean by the formal sum? It runs over all the index where the index set is finite. Now if we consider this like, okay, if it was finitely many, x1, x2, xn, we could take that function of xi. So it looks like linear polynomial. So this is nothing but like linear polynomial kind of thing. The coefficients is coming from some field. I mean ring. Here is a ring or field. So this sum finite. This is a finite sum. So it makes sense, right? We should be clear with that. Is it okay? So what structure it is having? It is having a ring structure again. So given a set, we can take the formal sum and the set of elements, because if we add two of them, then again it is a formal sum. So, and if we, okay, multiply by the ring element, it is again there. So it satisfies the condition of the group. Okay. So this group is called like chain complex, ith chain complex. Okay. So I is coming from the dimension of this simplex. So what does it mean? So n simplex, we had n plus 1 many points which are in general position, meaning that if we take n many points from there, they don't belong to the affine hyperplane which has dimension less than n minus 1. Okay, that is the definition of general position. So is it okay? The chain complex, ith chain complex, that was very easy. So we just took the set of all I-dimensional simplices from this collection. Then we made the formal sum, that's easy, with coefficient coming from this thing. And we said that, okay, we'll take this group. That is called ith chain complex. Okay, so what we can have from ith chain complex. Now, look at here. So if we have a simplex, then it has a boundary. So boundary consists of faces, right? Those are like, again, codimension 1 simplices. But how many boundaries are there? If we are having n simplices, then n plus 1 many boundaries are there. So we should have a orientation on that set. So this is A is I simplex. Okay, so this is I simplex. Now how many facets will be there? I mean codimension 1 facets. So if we omit one of the vertex, then we will get all the facets. So how many will be there? I plus 1. Now what should be the connection between them? So the connection, the relation among themselves is given by this relation. So if we say boundary, we could say that, okay, we'll take the sum, but it will not help us. Because if we take the sum, it will not be interesting. So what we take the alternating sum. So first we have to consider one orientation. Since we take the finite simplicial complex, we can give an ordering of the vertices of the simplicial complex, which will induce an orientation on each simplex very nicely. And then we can have this formula. Is it okay? So what we are doing, we take ith chain complex, elements from ith chain complex. Okay, this we can think as a basis. So this is the basis here. So from here, we have to define a map here. So how we are defining this way? You may think that, okay, there are other ways also. Yes, we can have many other ways, because from a simplex to its boundary, why we have to consider all the boundary? We can take the partial one and we can try to do whatever we want. However, the interesting things will not happen. What is that? The composition of these two may not be 0. But if we take this way, the composition of these two maps, boundary maps, it is called like boundary map, the composition is 0. Because if you apply the boundary here again, then you have to omit some element from here, then ij, so some calculation is there, it will say that the composition is 0. So that means zero, then you have to be like that, like that. Okay, that's a good question. I like it. You know, a question should come. Okay. So whether it is the if and only if condition or not. So how we can check that? We want to take like two simplex goes to one simplex, then one simplex goes to zero simplex, and we can check that whether we should have this. That's good. Thank you for asking. So what happened? So if I will answer your question. So if the composition of two maps, so this is homomorphism. As a module homomorphism, so this has a modular structure over R, and this has modular structure over R. So as a module homomorphism, this I will take few minutes to, because it's not that much familiar to us. So if the composition of two homomorphisms are 0, then what happens? This image of this one is a submodule of the kernel. Okay? That we studied in the homomorphism of groups or something, or homomorphism of rings. So this happens. So therefore, since it is a module, so it is a normal subgroup of kind of things. Quotient module makes sense. So that quotient module, we are saying that it is the ith homology group of the simplicial complex. Okay? Is it okay? The definition of ith homology group. So what we had, X is a simplicial complex, and then we have this chain complex. So chain complex is generated by the ith simplices, I-dimensional simplices. Then we had a map from I-dimensional simplices to I-1 dimensional simplices. So this is content. So if it is the ith simplex, what should be the map? So this map we choose. Question came, if the composition is 0, whether it is if and only. So we will check it a little bit. Is it okay? The definition okay? Up to this? This is little bit complicated. Okay, I feel complicated because it took me to realize why the definition of the homology group should be like this. It took some time for me, 2-3 months. Okay, so I will go a little bit. So how we understand mathematics? By doing computation. See, sometimes I tell my students that when we were in high school, we loved to do problem solving, so many problems. But when we come to BSc, then we feel, oh, we did too many problem solving, we don't want to do. When we come to MSc, it becomes more or less. I don't know why. For me, it becomes more and more because I didn't know many things. But students follow that, okay, I don't want to do the calculation, but here let's do some examples. So we take the boundary of two simplex. So it's like triangle boundary. So it has 3 vertices. So what will be the 0 chain complex? That will be generated by only 3 vertices because 0 dimensional. Okay. So and the 1th chain complex will be generated by the edges. So these are the edges. So now you can see we took the oriented edges. So this C1 is isomorphic to ZQ. ZQ means 3 generators are there and over Z. Okay, here the ring we are considering, that is Z. So it doesn't need to be filled. Okay, why this is trivial, why this is 0? Because in the boundary of triangle there is no other higher dimensional simplices. So the chain complex automatically it becomes 0. So the chain map, it will be like, if we just know this map very well, then we can get it. So what is this? So if we take this one, so by definition, okay, now the question is what it has to be, whether V1 plus V2 or minus. So if we take this plus, then the composition will not be 0. So therefore it is like if and only condition. Some other coefficient, if we put some other coefficient also like 2V1 minus V0, then also the calculation will say it is not 0. So therefore that is the if and only condition to have that composition of this boundary map is 0. So what will be V0 then? It is image of delta 1. So what is the image? Image is generated by these differences. So if we check, if we add these two, or subtract this, okay, these two, then we get these values. So these three are not independent, so they are dependent. And two of them, they are independent. Okay? As a module, they are like a module basis, they are independent. So it is two-dimensional subgroup of.
Why should the composition of boundary consecutive boundary be 0? That's what you said, because we found that we are looking at answering what he asked the question. So maybe you can address that why should the composition should decay?
Okay.
Why are we looking at that?
Okay, that's a good question. The thing is,
that is geometrically evident.
That is another way that why. Oh, good, thank you for asking it. So, if we have some topological object, what we want to know? Right? So, up to homotopy, how it looks like. Right? So, for example, if we have, bangles, we have this donut kind of things. So, how topologically it looks like? We can shrink it and we get circle. So, it has a hole. What about the higher dimensional case? So if we take our football, not like American football, but like European or like Indian way of we think, it's like a sphere. Right? So it has hollow things. It's not, okay, we can have solid also, but if we take solid, up to homotopy, it will be like contractible. So when we are saying that the composition has to be 0 in the sense, if we have something, right, whether this bigger set is affecting, so meaning that whether we have some dimensional voids there. So how to measure that void? The question is how we can find that void. For example, if we take sphere, then is there any one-dimensional set there which is not contractible? Okay? So how to measure that? Now, how we can think our sphere? You take the boundary of the triangle and you take the suspension, then you will get a simplicial complex structure. So from there, if we try to do the computation, the main goal of the computation is whether it contains some void, right? Whether it is empty or it is contractible, or how much it is contractible. So because of that, we have to have that condition. The composition has to be 0, so that the void things and non-void things, it will be, the contractible things we can contact in the quotient. So the boundary, if we just contract, then how many void things are there, it will compute. So that, thank you sir for asking this. So it says the collection of some simplices, and there are some. So that gives some topological objects, but other extra things we are killing here. So it will say the measurement. So like if we have this circle and this one, if we kill that, so we'll get the measurement of the void. So how much it is there? Okay. So that's why we needed the composition. So how many? So in ith dimension, how to measure that one? Because of that, the composition has to be 0. So that means here, this is a sub-module of this one. It should not be, it should be killed. The extra thing should be killed, and the exact value should be remaining. So this measures the how many voids are there in this space. Okay, good. So here it is 2-dimensional. only subgroup, but it is a direct summand. Okay, so this is two-dimensional, and if we consider the zero chain, so that will be generated by all these three. So this will be isomorphic to Z3. So what will be the zeroth homology? It is nothing but Z0 quotient by B0, so that is Z. Actually, this is most of the cases, and this counts the number of connected components. So if it is connected, if the simplicial complex is connected, then it is always Z. So what about Z1? Okay, we take a one cycle. So one cycle meaning like formal sum of that. So we take N V0 V1, N V1 V2, N V0 V2, and then what condition we are having that okay, we take this sum, but whether it creates some one-dimensional object or not. Right? So it creates one-dimensional object if it satisfies this one. So if we have that, then we get this one. Now we will have this relation. Now we can easily take that from here. What should be the value of L? So M has to be equal to L, N has to be minus L. So this minus sign automatically comes. So because of that, we have to take the alternative sum. So that's like some kind of disadvantage. Okay. So any one cycle will be looking like this. So that means the one cycle is generated by this one. And what is B1? B1 is coming from image of C2. Right? But C2 we know that 0. So if we have a 0 module to some other module, the image will be always 0. So B0 is 0. So the quotient is Z. And other homology is like 0 because the cycle, k-dimensional cycle automatically is 0. The quotient is like 0. Okay, so that is the computation for the homology of circle. And we can see it takes some time to do the calculation. Now if we have to do some little more complicated things, so that natural question will come, what is the homology for n-dimensional sphere? So if we think it as a boundary of n plus 1 simplex, then computation is little bit difficult. But is there any other way to do that? Then the answer comes from different ways. Is it okay? Concept of homology. So what we had data set. From data set we had graph, and from graph we had simplicial complex. I didn't say that how we can get the simplicial complex, but we discussed before that. We discussed the concept of simplicial complex. Okay. Now the important part of our life or of this talk, it says if we are given data set, then how we can get the simplicial complex structure. So what we are considering that this is a subset of some metric space. Metric space means some distance function is there. It can be Euclidean metric, it can be other metric also. There are several ways to do that. We know several types of metric, right? So this is a subset of this one. So if we are having a metric, then we can have this kind of subset, which is like a ball of radius epsilon around this. So if we have two balls, this one or k many balls of radius I epsilon, and if their intersection is non-zero, then we can say that okay, we will consider this set as a k minus 1 simplex. Because we are having this set, and their intersection 0, so that means it is like filled up, so the concept makes sense. Right? We can define it, but whether it will be meaningful also. So in the next slide, we will see that it is meaningful in some sense. Is it okay? So this is called like check complex at level epsilon. Is it okay? So from data set, how we get a simplicial complex? Now you can say that how to determine this rho. That is the important part in our machine learning. So if we have to do the exact calculation, suppose we are having 3 points or 4 points, right? So if we take it as a square, then whatever simplicial complex we will get at epsilon level, if the 3 points are very near and 1 point is very far, the corresponding simplicial complex will be different. Therefore, this metric, choice of metric is very important in our data analysis. If it comes very naturally, then it's okay. Otherwise, we need to find a method. Okay. So, in topology, what we know, if we are given a metric space, so that means it is a topological space and it has open subset. So we can define open subset. So we take the collection of open subset. If that open subset satisfies a similar condition, oh, there is a mistake. So it will be UIK. Sorry for this typo. So it has to be UIK. If that intersection is non-empty, then we will say this is a like simplex. Okay? So we will take this collection of simplex and we say that this is a simplicial complex called the nerve of this covering. So what is the information connection between this simplicial complex and the previous one, complex? So that is called the nerve theorem. So if we take this collection of open subsets from this topological space, which satisfies this condition, that if we take any finite collection of open subsets from collection from there, their intersection should be contactable. Now it comes the concept of contactable. Either it is empty or contactable. So, like, if we have this open set, it's filled up, so this is contactable in the sense like we can push it to a point. Okay? We can shrink it to a point. However, if the open set looks like this, and these two, so this is U1, this is U2, their intersection is like this two. So we are not considering this part, so this is okay. So if we have this kind of situation, then it is saying the space M we took, that is homeomorphic to the geometric realization of this nerve complex. Okay. So nerve looks like simplicial complex, it has nice structure, but topology may be like, something complicated or crazy. However, they are like homotopically equivalent. So what does it mean by homotopically equivalent? It's like we have map from x to y and c from y to x such that this composition, this composite C is homotopic to identity on y, G composite F is homotopic to identity of x. Okay, so in other sense like their topological properties are same. Is it okay? So this is important thing. So from the data we get a simplicial complex and we can say what we can do it with that. Is it okay? So this is important theorem in that topological data analysis. Okay. So what we are considering is check filtration. So what does it mean? So we took some point set, so that means data set, and the metric space is the data set, and we will take the, so if you have some set like this, suppose the shape of the data is like this. So how to get it? So we'll get this one using check complex for the computational purpose, but if we take the neighborhood, then what we'll get, it will fill up. We'll get like tetrahedron kind of things, but we should not be up to that. So how far we should go, so that means what choice of this epsilon 1 or epsilon n we should have. It depends on the shape of the data, but how to determine that? Our goal is to determine shape of the data, right? So we have data set, so we will make these complexes one by one. So the difficult part is to say or find this epsilon 1 such that this set will give the exact shape of the data. That is one difficult question in topological data analysis. If we get this, that okay, this is the data set, and if it happens, then we are happy, but how to determine that epsilon n? Okay, so one of the good problem, how to determine that one. So this is one example. So I just took it randomly. You can see that, okay, if I take these two nearby, and this is little far, then we will get this shape, because we are considering the open subset here, open ball here, and they will intersect. These two open balls will intersect before these two are intersecting. And the intersection is like contractible. We took the Euclidean method, so we get this one, then this one. Now, this gives the full simplex, right? But we may have to stop here, because data set may be up to this step. So topologically, I mean, this construction is not saying where to stop, but it gives the construction. At some point, we will get the data set. But how to build the data set from the, simplicial complex from the data set. Right? So there are some algorithms. It is now available. That is very well known. That is called mapper algorithm, and computer can do it. Okay. So what it is doing, see, this data set is like this, circular. So it will take some cluster. Before that also, there is another method that is shown, they use it, that is called like principal component analysis. So if the data set is very huge, they will take little, so they will do the dimensional reduction. They will come in little bit lower dimension, and then they will find this clustering. They will do this clustering. So there are 4. This is a very easy example. So 4 clusters. Each cluster will give one node, and if they are having intersection, then there is an edge. So this algorithm says that what should be the graph of that. So now we have graph, and if we know the metric, in 2 slides before that, we showed that if we are having metric, then we can have a filtration, check complexes. And now, if you love the computer language, then the question will come, how to put that information in the computer language. Okay, topologically we can do, but how to make it in computer language. I think for the check complex it is there, and this complex also there. They are related. Okay. Okay, up to this, okay? From data how to get the graph, and graph how to get the simplicial complex. And simplicial complex is a topological space. Then the easiest things to compute in topology is the homology group, not the homology ring or like fundamental group. So that is because of the definition. And what it finds, as Professor Tarun Kumar Das was asking, that what it means. It means that how many whites are there, we want to find out. So that is the homology, computed homology gives the answer. Okay. So, is it okay? Now you can try to, if you love computer language, you can try to find out some coding which will say how to find out the second homology or third homology of a simplicial complex. And then the question will come, okay, you will have algorithm, whether the computer can compute it, meaning like how long time it will take. Whether you can give the fastest algorithm or longest algorithm, all questions will come. Okay, so we have this Rth at Rth stage, so that means this R is epsilon. So at that Rth stage we have this simplicial complex, check complex. So if we take the kth homology of that, that is called as kth persistent homology at the Rth level. Okay, so we know the concept of homology, we know the concept of check complex, and we are just defining it. Okay, this is the kth homology of the homology group of this check complex, Rth level check complex. So what it measures, so why R is like when we are moving, that epsilon we are moving, right? So we have data, we wanted to understand the data set, so we try to have the simplicial complexes from there, but how far we can go. So if we go slowly, that how to determine the shape of the data? By computing its homology, that how many holes are there inside the pictures. Okay, so that will determine the shape of data, because after some time it will be up to some like k-dimensional sphere can be fit into that, which cannot be contactable. So that is measured by this state homology. Is it okay, the definition? So that is the good thing. How much time I have? 2-3 minutes? Okay. So is it okay? So that is called like persistent homology. Why is that? Now, so sometimes one hole will come like white. Now, after first time, it will be killed. So that means it will be contactable in higher dimension or not. So that is called like birth and death. So that birth and death, we can represent it by some bar representation. So that is, those barcodes are called like persistent barcode. And persistent diagram also will come for a given data set, and the filtration, one can record these intervals as a persistent barcode, and then the 2 points B, D, it can be put as a like point. Right? If that point is very far from the diagonal, then we will say that it gives the real feature of the data. So that means that white, like in the data set, in the shape of the data set, it is all remaining for a long time. Okay, so we have data set, so this is C0, and then what bar is have this many bars. So if we have this one, some of them are remaining and some of them are disappearing. Here we have 2 holes, here we have 1 hole, so it is remaining there, and there is nothing here. So corresponding to this observation, we will have this point. So this represents birth and death. So here is death and this is birth. So that is known as persistent diagram. There are some good things. So if this point is very far from here, this diagonal, then we say that the data shape is kind of that. So that means in that dimensional white is there all the time. Okay. Okay. So I will discuss what are the concept and methodology in briefly. So it is like we take the shape, or we will try to understand the shape of the data point cloud, of the point cloud. Right? This can be multidimensional, whatever geometric shapes are there. Okay. Okay. Then from that data set, we take the persistent homology. So it says that how the shape of the data set behaves. Okay. Then we get this one. So this is important because then we can compare. So for example, if we are having normal cell, cancer cell, and normal cell, then no need to study. But at least we need to study and see that what are the properties it is having. And if we have cancer cell, then also we need to have collect some data and compare them. So how we can compare them? So we will get 2 different persistent diagrams, and there are some methods to compare these 2 persistent diagrams. That today I am not going to say because so many things. And mapper algorithm, it gives like, it creates one-dimensional graph. So how many questions can be? So it can be applied in many places. Okay, if it is very noisy data, sometimes it is difficult to understand using classical statistical method. Like if we have data set in a circular way and we get the regression line, we cannot get the more information, we cannot conclude that much. However, if we study this topological data analysis, we can say that, okay, this shape is like this, the property of that one. So we use dimensionality reduction such that it will not change. The property of the data will not change. So it is now applied in many places. So in genomics, material science, image processing, and here we can see that how many open problems we get. We know that topologically we know the algorithm, but how to fit it in the machine language. And whether the fastest, how much fastest it will be. It is amazing. So we have topological side, what type of metric we should choose. Then if we that is crucial part. And then what will be the homology calculation, and if we do the homology calculation, what are the methods? See, doing calculation for first, second, third, I think up to third, I know that it is known. But if we have to go, I don't know any other algorithm which can be fit in and check in the machine. So that kind of things are there. So many applications, almost everywhere these are happening. So what they are doing, they are comparing what is the differences between their persistent diagram. Okay. And the bad part in the sense like if somebody wants to do it, he or she have to know so many things. Topology, graph theory, and the places where you can apply, and the tools also, this C++ and Python. So during my MSc, my teacher wanted to teach me C++. When I saw the algorithm, I said, sir, this is very easy, I don't want to do that. But now I can see it is not easy, it is also complicated things if we have to use this one. So you can see if you have to do the topological data analysis, you have to be also robust, like the application. So many things you need to know, and there are, some references I just included. So it started around 2002 or 3, then many applications are happening, I think, what is it? Gunnar Carlson and one of his students, he was doing some other things, and then Zamordin, I think Gunnar Carlson and Zamordin, they started. It was around 2002 or something. But in this paper, if you read this, it will be very difficult to understand, but you need to read so many papers to get the idea. Okay. So, several applications. Here we can see in order network, cryptocurrency market, maybe here also some other, where is that? Industrial challenges. So we love to have industry in our mind. Here is like something related to black hole images. There you can apply some medicine studies, and here like neural network, lost landscape. So many areas, it becomes like very hard. In the last 25 years, I mean in the beginning, 10 years, it was going very slow, but now it is blooming like anything. Like here the cancer, cell, digital marketing, information space, functional data analysis, whatever this outcome. My problem is, if I have to do this, then I have to know the other areas, like biology, which I don't know. So that becomes like problem. So here biomolecular properties prediction. However, if you know something, structures, okay, so many applications. And